Hello, ma'am. Hello. Good morning.
Yes, hello.
मैम ये सर्टिफिकेट कैसे मिलेगा मैम? मैं तो YouTube से देख रहा था, जो आज फर्स्ट टाइम मैं जुड़ा हूँ आपसे।
Yeah, attend the course and concentrate and gain some knowledge, and you will take
Yes,
your
sir.
attendance. Don't worry about that.
Thank you, ma'am.
Okay. So, very good morning to all the participants. We are going to start our first
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Good morning, ma'am.
Okay, so we are going to begin with our first session, and our today's expert is Dr. Shashi Narayan. Hello, Dr. Shashi Narayan. Hello, sir.
Hello.
Yes, very warm welcome to you, sir. So, shall we start, sir?
Sure, ma'am.
Okay. So, first of all, I heartily welcome our today's expert, Dr. Shashi Narayan, and I will begin with his introduction. Dr. Shashi Narayan has gained Bachelor of Technology in Civil Engineering from Malviya National Institute of Technology in 2010. He has completed his Masters in Structures from Indian Institute of Sciences in 2013. After completing his Masters, he joined as Assistant Professor at Manipal University, Jaipur. In 2014, Dr. Shashi Narayan joined NIT Uttarakhand as Assistant Professor. During his tenure at NIT Uttarakhand, he obtained doctorate from Malviya National Institute of Technology, Jaipur. He has contributed to the field of finite element method during his master program. He has been a part of various projects sponsored from DRDO, ISRO, NULL, and he has also contributed to the field of earthquake engineering. His major research areas include finite element modeling of structures, energy-based design of buildings, response of structures during an episode of earthquakes, designing and retrofitting of structures to resist seismic forces, and nonlinear analysis of tunnels in stratified deposits. Today, Dr. Narayan is going to give you the presentation on behavior of building frames during an earthquake. So very warm welcome to you, Dr. Shashi Narayan, and now I invite you. So over to you, sir.
Thank you, ma'am. Good morning, all. I will be mainly discussing the behavior of building frames during an earthquake. In this, I will be first discussing what an earthquake is, how it is generated, what are like foreshock, main shock, and aftershocks, and then we'll come to discuss how the building frames are analyzed during for an earthquake. In that, we'll be discussing pushover analysis, that is nonlinear static analysis. Plastic analysis we will be discussing. Some part of that we will be discussing how there is the joint cancellation and all those are taken care of during the plastic analysis. Then we'll also be discussing how experimental analyses are done for an earthquake. I hope some of the organizer have my number. If I'm not audible or there is some connection issues, let me know in between. Okay. So
Yes, sir.
Will we sir, ma'am. So we'll be discussing mainly the first elastic rebound theory, then the magnitude of an earthquake, what it is, and how that energy content are like related with the what we say of the Richter scale magnitudes. Then we'll be discussing the earthquake waves, the seismic map of India, like where what map is there, like how it has developed since 1964, then 1983, and then 2000, then 2016. How different maps have come up, what changes were made based on the past earthquakes. Then we'll see the effect of earthquakes, and then we'll also be seeing the analysis of the building frames. So I hope all of you are aware with the elastic rebound theory. Elastic rebound theory is like there is a friction between the two plates, and with the motion there is an energy stored between them, and once the energy is stored in the string is more than that of the frictional forces, that is the resisting force which is there between the plates, then there is a release of energy, and this release of energy is generating the earthquake. And that earthquake is like what we hear of recently, what we have heard in the Punjab region, nearby Chandigarh. There was an earthquake of 6.1 magnitude. That is that is mainly due to change in this energy release. Similarly, sometimes what we see that there are one earthquake is there, and then after some time of the first earthquake there is a second earthquake, like the recent one. There was an earthquake in the Hindu Kush region of 6.3 magnitude, and then there was this earthquake of 6.1 magnitude in this our Chandigarh region. So what is happening in that case, that there is one energy release, and due to that energy release there is a strain energy developed in the rest part of the plate, and that rest part of the plate again releases the energy, and that is why we hear that there is a one earthquake at one region, then there is another earthquake in the nearby region. And these small energy release is sometimes very beneficial, that due to this we are not having large earthquakes. That is, we do not have a big earthquakes. Like if there had that, this energy would have not been released, this energy would have been accumulated, and that accumulation of the energy would have resulted into a larger earthquake rather than this small earthquake. So if we look into the strain versus time graph, that like fine sand is fine sandpaper, that is the frictional forces between these two are lesser, and the frictional forces between the other two are large. That is when we have the coarser, that is the frictional coefficient is large. Then you see that there is energy developed. If we look into this nicely, the graph, that you see there is energy developed in the first one. There is energy developed over here. This energy developed, we are taking off. We are saying that this energy is being developed, and then there is a release of energy. Then again there is a movement, and there is again energy developed, and then there is a release. This one we have, and then you see in this region, the first one there is a small energy release. Due to this small energy release, there is a energy stored in our second region, and there is a large energy release whenever there is a change in that. So this energy releases generally is in terms of earthquake waves. Earthquake waves in the sense we have P wave, S waves, and surface waves. So like if we talk of the P wave, S wave, and the surface wave, then what is there? That first the P wave strikes, then the S wave, and then the surface waves. P wave is the least devastating. You see that there is a very less amplitude changes. Then there is a S wave. S wave has time, but then also this magnitude is somewhat more than that of that. The amplitude of the vibration is more than that of the P wave, and the surface wave is the one which is most devastating. And this goes with the attenuations based on the site soil data. And this is the P wave, that is the time taken between P wave and S waves are generally used to determine the epicenters. I talked of the attenuation, that is due to the site to the source location. You see, if there is a solid rock, or then there is a less vibration. In the poorly consolidated sediments there is more, and in the loose sands there are much more. Like you see the first seismograph is in the bottom part. Here we have the first seismograph on the like that of the solid bedrock. Then the second seismogram we have of this the poorly consolidated, and then the third one. So we see that each, like as we go on changing the soil type also, there is a change in the magnitude of the vibration that we see. Then we have talked of the P wave and S wave. Due to this, you see there are different points where this the location of the our movement or the energy released is there. That is the epicenter is there, and these all will result into some wave, and that will have some time that will take to reach our site. That is the location where we are recording. And if we plot all the points of location of P wave and S wave, we will get to understand that how far the distance is. This is the farthest point, these two are the farthest point, these two are the farthest point, and these are the one which are very near to this. So you see that in this the P waves are reaching at a slower, the distance between P wave and S wave, time taken between that two is increasing with the distance between the source and site. So these are the ones which we are used to determine that how we have the location of the earthquake. The energy of the earthquake, the energy content of an earthquake can like be analyzed or can be understood with that of the strings. Like if you can think of the Spaghetti strings. One string, if you like bend what will happen? If you try to bend this, they will try to first have the energy, and then once there is a breaking of that, if you start to bend it, there will be energy stored, and when there is like much more energy, it will break. And when there is a breaking of this, there is a vibration in the string, and that vibration in the string is the energy that is released when this elastic, when there is a energy stored while bending, and this energy released is causing our vibration, and that is similar to that of an earthquake, like if we talk at a lower value. Now, if we think of this one string as magnitude 5, then 30 times that of that means if the energy required to break 30 string is my magnitude 6. That is, each magnitude change is like there is a 30 times energy change. And if we go with the like M7, we'll have like 900 strings. That is to be like the energy is released while breaking this 900 strings. And similarly, we go on 8 will have 27,000. If we go with the like M9, then that is 729,000. So that is like with each magnitude increase, there is 30 times energy stored. So what I started with the like lecture that magnitude 6 and all are small earthquakes. That is why we are able to like with small energy releases, we are somewhat having that large, we are avoiding the large earthquakes. If this energy is stored and go on in like accumulations, then finally it will break, and it will break with a larger value. That is, the larger energy release will be there. So based on these, like the location where this earthquake can be, what can the magnitude of an earthquake can be there at a location, at a site, we divide the Indian map in like 5 different zones. Zone 1, Zone 2, Zone 3, Zone 4, Zone 5. Zone 1 is like very less probability of having an earthquake, and that also if there is an earthquake, that will be of a lower magnitude. Zone 2, it is like thought of a higher magnitude. Zone 3 higher than that of 2, Zone 4, and so on. Now, based on past earthquakes, like 1984, this was the map where we had Zone 1, Zone 2, Zone 3, Zone 4, Zone 5. Then after that, there was in 1984 there was a earthquake in the Bihar region, Bihar Nepal border, and then there was one earthquake in the Assam northeast region as well. So these two regions, and nearby we had a Latur earthquake. So all these three earthquakes had resulted into again rezonation of the map, and then once this map was developed, and then we had in 2000 we had a Bhuj earthquake, and Bhuj earthquake was the one which had like led into so many research development in India after the Bhuj earthquake, because that was one which was very much devastating earthquake. And based on that, then again in 2002 we had like removed the zone 1. That this zone 1 is now we have only 4 zones: zone 2, zone 3, zone 4, zone 5. That is, there is no place where we cannot expect an earthquake. And based on this zoning, we have a PGA levels defined. And in 2016, the earthquake code has been revised, and based on that, this is the new earthquake zoning map. And based on each zoning map, there is an MSK intensity. This is not same as that of the magnitude which we talk of, that Richter scale intensity. What we talk of like a magnitude 6, magnitude 6.1, that is on the Richter scale. We are here discussing the MSK intensity. This intensity is more into taking into account not only the energy release, but also the effects that an earthquake is having. Like MSK intensity 9 will have like there is a structural variations are there. 8 there is non-structural elements are failing, and so on. That is the like 6 there is no failure, there is no life loss, and that way we have defined the intensity. That is the new intensity which has been adopted in 2016. And other is that the effective PGA, what we can like the other standards like the American standards or the European standards call up the maximum considered earthquake. That is the PGA level of the MCE, maximum considered earthquake, is our 0.1 G for zone 2, 0.16 G for zone 3, 0.24 G for zone 4, and 0.36 G for zone 5. And design level earthquake, when we do the analytical analysis, we try to make it by SA by G into Z by 2. So design level earthquake is half of this effective PGA which is there specified in our earthquake code, that is IS 1893. And in one more thing very important is that our earthquake demands, like based on these, we have a earthquake demand spectra, that is the SA by G versus time period, that is the time period of the structure. Each that we all know that the earthquake actually is a displacement of the ground rather than the force. What we try to get that with that displacement, we get a corresponding force which is to be resisted. So this force resisting and this demand is based on the time period of the structure. If time period is larger, there will be lesser force demand, that is SA by G will be lesser. Where if we have like nearby less than 0.25 or 0.3 seconds, there will have higher demands. And moreover, we have already seen that this also depends on our type of the soil which we are taking. That is hard rock will have the higher lower demand than the medium soil, and then the soft soil. That we have already seen that based on these soil conditions, this goes on changing. Typically, time period of the structures which we are taking into considerations are like single story building is 0.5 seconds, 0.05 seconds, low rise building 0.4 seconds, 15-story buildings 1 second, reinforced concrete chimney is 2 seconds. So as you see that as we go on increasing the time period, we have already seen that the SA by G will be lesser value. So So based on these, the time period, approximate time period of the structures, we determine what will be the SAYG value for the structure. So now we have, actually we have three things that is taking into account. One is the zone factor, that is which zone the structure is. Then the second thing is our, the soil type, which soil type it is, and the third is the structure which is there. Then these all three combined will give me a force demand of an earthquake. Before moving to that, we will also be discussing like what does that means, that if we have like 0.1 second, 0.2 seconds, so which type of earthquake will be like affecting more than the more in the smaller building or the larger building. So there are like right now in this consideration, there are three different type of building frames. That is, one is having a smaller length, the one is mid-rise, and the third one is high-rise building. So high-rise building will have higher time period, mid-rise will have lower, and the low-rise will have very low. So like if we have low frequency vibration, you will see that the tall buildings will vibrate. You see one thing, that the tall building is vibrating, whereas the other two are not vibrating. One of the example of this is the Japan earthquake in 2011, where low frequency vibrations were observed. Then now if you move somewhat faster than that of the one with this, then you see that the mid-rise buildings are vibrating, whereas the low-rise and the tall buildings are not vibrating. This is an example of Mexico City earthquake in 1985, whereas one of the that mid-rise buildings failed, whereas the low-rise buildings or high-rise buildings did not fail. And that in this Mexico City earthquake, there was also like the loose soils in the Mexico had resulted into a frequency frequency filter that acted as a frequency filter, and due to that also we had like low mid-rise building failing rather than that of the high-rise and small buildings. Now if we move more faster, like very fast high frequency, if we have, you see that the low-rise buildings frames are having higher demand, whereas the other two are not having that much of the demand. So now there is the fourth effect which is there into the, when we are considering the earthquake, that is the frequency content of the earthquake. And that cannot be like predetermined, like what to do the frequency content and all this. For this we need to go with the nonlinear analysis. If we need to, like the other thing, three quantities, that is the site condition, the zone factor, and our site condition, zone factor, and structure time period, we can go with the linear analysis or non-linear analysis, but we can go with the static analysis. Whereas the third quantity, that is the resonance effect which comes into the vibration, for this we need to go with the non-linear analysis, that is non-linear time history analysis or the experimental analysis which we need to do. How are the effects of an earthquake, like how it affects the building frame? There is an acceleration we have at the bottom. This acceleration will lead into a displacement of the foundation. There is a mass, a large amount of mass at the top. This will try to remain in its position. So there will be a movement in the ground, and the roof will try to remain its position. So with that, there will be some differential displacement, that is the top, the roof and the foundation there will be a the displacement between the roof and the foundation, and this will result into an inertial force. That is the roof will now try to come into its mean position, that is it will try to make the columns straight. So there will be an external force, inertial force acting, and that is the force which needs to be resisted. The other two forces, that is our elastic force, that is due to the elastic stiffnesses of the columns that is coming, and one is the damping force. In addition to that too, we'll have now inertial force coming into picture because of the motion, and that inertial force will be depending on the acceleration of the ground, that is our earthquake shaking. what is the design philosophy? What we have, like our design philosophies are such that whenever we have a small earthquake, our structure is safe. Or minor shaking, the structure is safe. There is no damages or damages only non-structural elements. Moderate shaking, we have damages in the structural, non-structural element, and there are some locations where we have hinge formation. That is the element has gone into a plastic zone. That is the element has gone into non-linear zone. In this case, like the one which we have shown, the one of the beam has gone into the non-linear range. For a stroke, shaking is more like we have life safety. The structure fails. That means that there is a large deformations. The structure does not fail in the sense that it still bears the strength. That is still the structure is standing, but it fails in the sense that there is large deformation and like there is a serviceability failure rather than the strength failure. In the strong shaking also we want that the serviceability failure is there, not the a strength failure. And if we have serviceability failure, there is a less life loss. Whereas when we have the strength failure or the brittle failure, then in that case we have life loss more than that of the structural loss. So our aim is, our aim in while designing is that we have less life loss, means we avoid life loss, and the structure fails in like one of the earthquake. It is like we cannot predict the earthquake. We always have like there is always a chance that there will be an earthquake which will be severe than that of the previous earthquake, and then that structure will fail. But what we want that in those type of earthquake, our structure sustains. That is for the building right now. But when we go with the like important structures or some structures where we have like nuclear power plant, that is always in the elastic design. We want that the nuclear power plant is always in the elastic limit. We do not go with that there is a plastic limit, it goes into plastic limit also. We always go with that nuclear power plant will be always in elastic limit. So all these taking into consideration, we have a factor that is coming into picture, that is a reduction factor. We want to take into account that is the plastic, that is the non-linear behavior of the structure. That is the structure is generally we are not assuming it to be elastic, but we are assuming it to be non-linear. So for a small demand, the structure is safe. For large medium demand, that is somewhat more than that of the elastic limit demand, the structure is still safe. And for very large earthquakes, the structure fails. If we talk of the elastic design and this, there is like if we draw a straight line between the, if we draw a straight line from here to here, then this is like approximate demand which is expected out of this. But what happens that if had it been we design into an elastic region, but what we do, we design it for, rather than this, we design it with a strength reduction factor, and we design it for this. That is, we are taking into account the non-linearity. Similarly, if we have a large displacement demand, we will have a very large force requirement. This is the force requirement. But if we take into account the non-linear, there is a reduction factor of this. So this is taking into account our ductility requirement. That is the ductility requirement. For that we have a reduction factor R in our code. SA by G into Z by 2 into I by R. That is importance factor is multiplied and reduction factor is divided. So based on these, we have like our codal, we have our force demand with that of the earthquake. So this R is mainly like what is happening to our ductility requirement. That is, this R takes into account the ductility requirement in the sense that if we have if ductile, it is more ductile, we can have a larger value of R. Like for the moment resisting frame with the ductile detailing, we take a value of R as 5. So, and if it is brittle, we take shear frames. We take a lower reduction factor, because that there we have a brittle failure rather than that of the ductile failure. So, what is actually a ductility? Ductility is generally defined as like the ability to deform beyond its elastic limit. That is, if we have a ductile material, that means that it will be deforming more than that of the elastic limit. It will be deforming more than that of elastic limit, and the ratio of the final deformation to the elastic deformation is your ductility ratio that is defined. So based on and this ductility, the least the whichever is the least strength material, that is the link which is the weakest link, the ductility of that weak link will define will govern the ductility of the whole structure. Suppose we have suppose we talk of the beam column elements. Okay, suppose we talk of the beam column elements. If we have a strong column, weak beam, the ductility of beams will govern the ductility of whole structure. If we have a strong beam, weak column, ductility of the columns will govern the ductility of the whole structure. Before this discussion of this, we're discussing one more thing, that is the confined concrete and unconfined concrete. The one curve which is like after sigma c that is coming down, this curve is of the unconfined concrete. That is the concrete in which the shear stirrups are not there, means lesser amount of shear stirrups are there, such that the concrete is not confined. If the concrete is confined, there is a larger the ductility. There is a large amount of that yield to this ratio is large. This ratio will give us mu value. Moreover, the deformation is such that it takes into the slope of this is the post yield slope is lower than that of the unconfined concrete. That is why we have whenever we do with the concrete, we go with the ductile designing. That is we want that the structure should be ductile, and ductile designing mainly is concerned with the if we have the holding the bars is into there is a shear stirrup coming into picture, and this stirrup is bent and such that now what will happen when there is a this is our whole section, this is all concrete. So what will happen if we apply compressive force on this? What will happen? This due to the Poisson's ratio, we will try to increase this side, and this increase will be resisted by that of the shear stirrups that has been provided. So so based on this, what happens mainly when we have we apply compressive strength, there is a if there been not been this, there had only been this, what will happen? If we apply compressive strength due to our Poisson's ratio, this will increase, and that will bring in tension in the material, and that will fail. So when we have a shear stirrup, what will happen if we apply a force due to Poisson's ratio, it will try to increase in the lateral direction, and which will be holded by the shear stirrups which is there. So large amount of the failure will increase. Generally it is seen that for M30, for the confined concrete, we can go till 43 MPa. So that is the very large amount of increase in the force. Also compressive strength carry capacity of the material is also increasing. That is what we see. Sigma c is over here, that is normal unconfined concrete. Sigma cp for the confined concrete is larger than that of the sigma c. Based on these designing, that is if we go with the ductile designing, we want that our beams should fail, not the columns. There is one more reason for that. That is why we go with the strong column weak beam design. One of the major reason for this is that beams, if fails, the failure will be localized. If this beam fails, then there will be localized failure only here. But if this column fails, there will be a failure of the whole structure. So for that also we want to go with the weak beam strong column. Moreover, we want the column such that this joint fails rather than this joint. So generally what is taken, if we talk of the moment carrying capacity, generally it is taken more than 1.2 times that of the beams. That is, the moment carrying capacity of the column is larger than that of 1.2 times that of the beam, adjoining beams. So this column has to be 1.2 times of this plus 1.2 times of this, the other beam. So it is like 2.4 times that of the beam. One more thing, like general perception is that if we talk of the strength, only the core of the concrete will take the strength. That is the strength, that is the concrete which is inside our shear stirrups. Others are only for cover. This is the major region which is resisting the forces. This region is not resisting. So this is like, if we go with the smaller columns, the ratio of material that is we are using for strength requirement and that of the total material used is very low. Like if we talk of 300 by 300 section, suppose this is 300 by 300 section and we give a cover of 30 mm, 25 mm, so this will become a 250 by 250. And now if you divide this, the ratio will come out to be 625 upon 900. So this is like 60, like nearly your 70%. But if this column, if we increase the size of the columns, if we, instead of 300 by 300, if we take 500 by 500 column, and we have again 25 mm cover both the sides, so this will become 450 by 450 upon 500 by 500. So this will give us 80%. So by just increasing the size, the material which is used for the strength carrying capacity is being increased by 10, almost more than 15%. So that is also why we want our columns to be like larger size columns. So what we want, generally we want at least 6 to 7 meters distance between these two. That is, the span of the beam is approximately 6 to 7 meters. So this 6 to 7 meters span, if we do not have, suppose if we do not have, then what we are having large amount of concreting to resist small amount of forces. So in order to have, like for economical design, we want to have 6 to 7 or 10 meters nearly of the beam sizes. So in that case, what will happen, we'll have a good percentage of the material which is being used to resist our forces. So if like architectural design is such that we are not having this, we are not getting this 6 to 7 meters of, like 6 to 7 meters is generally 18 to 20 feet. So generally what the room sizes we have is 10 by 10 or 12 by 12. So instead of having a column in between the two rooms, better to have columns at the ends only. So that is also one way which we can go with the design for the earthquake resistant. So what we have discussed for the strong column weak beam design, that is there should be both the thing. That is, the strength should also be strong as well as our stiffness of the column should also be large. So that if we have a lateral movement, then there is a failure in the beam ends rather than that of the column ends. This is very important point of like whole design of the earthquake resistant design of the structure for the building frames. We do not want these. We do not want that the strength of column and beam is same. We do not want that the strength of beam is more than that of the strength of the column. We also do not want that the stiffness of the beam is more than that of the column. So this is what we desire to have. So these were all the design constraints and all those things based on what we design. Now, once we have designed our building, there are different standards to analyze the building frames. There is one of the method which is based on the code, that is lateral force method or model response spectrum method. The other methods are that is not in our Indian standard codes. It is plastic analysis, post-shower analysis, that is for the, based on the quasi-static, and for the dynamic analysis, that is time instant analysis and incremental dynamic analysis. What we are going to discuss today mainly is the quasi-static method, that is plastic analysis, post-shower analysis, and also we will be discussing what experimental analysis are there. Before that, we'll have a look on the what linear elastic methods are there. So generally in the equivalent lateral force method, we try to what do? We try to get the shear forces that will come in the columns. So that is like if we look into closely what we have. VV, that the base shear will be equal to the total structure into acceleration in the lateral direction. Its movement in this direction will give me the shear force. That is mainly related, this is mainly given by the inertial forces. In this, we are not considering the other forces, that is that is the restoring force and the damping force. While calculations, we are mainly considering the inertial forces. So this mass of the structure, the total mass of the structure, can be given by W by G, that is the weight of the structure upon G. So this can be like made into W into A by G. So what we have in our code is W into AH, and for AH we have our codal provisions. This W is like seismic weight. This is not the dead weight, it is seismic weight, which is like the probability of what weight will be there when there is an earthquake. So we take some amount of the dead load and some amount of the live load as well. Like in the code, if you see that if there is a live load of 3 kilonewton, we take 50%. If more than 3 kilonewton, we take 25% of the live load into our seismic weight. What actually seismic weight is? Seismic weight actually is like the what load will be there on the structure during an earthquake. Like there are some part of the live load which will be there. That is why we take some part of the live load into the consideration of while we have the weight calculations. This A by H is equal to Z by 2. Z is your zone factor, and by 2 will give us the design basis earthquake. SA by G is function of our soil type, time period, and damping as well. That because the spectrum code which we have is based for the 5% damping. If we consider lesser damping, there is a modification factor given in the code. For that, you need to make a modification over here. Then I by R, type of the structure and the importance of the structure. This will give us the I by R ratio. That is if it is like a hospital building, I will be 2, then this ductility requirement is coming into R. So if we have ductility or overstrength requirement, then this is like nearly 5 for our ductile design. So this whole A by H is the function of what all? Time period, that is the natural period of vibration. Then the damping, mode shapes. Not actually the AH is not but this VB distribution is taking into account the mode shape of the structure. That is for the free vibration what the modes are coming. Then the type of soil structure and the place, that is this zone will come into your Z, and type of soil governs our type of soil governs our Am I audible?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Type of a structure will give us our type of structure, and the place will give me z value, that is the zone factor. The type of a structure will give us our importance factor and the time period. This will also govern the time period. The subsoil condition comes into SA by G formula, and the importance of a structure is also there. So all taking into all this count, we have got an empirical formula. This is an empirical formula. This has nothing to do with our any mathematical background or any Newton's law of motion. This is an empirical formula which has been based on the our probabilistic analysis has been developed, and this VV equal to W into AH will give us our this gives us a base shear. So if we take off a 1.25 seconds, SA by G comes out to be nearly 0.75. If we think it of for a hard rock, and if we think it of a zone factor 0.36, so this will come 0.18 into 0.75 into 2 by 5 for a importance factor taking 2 and a reduction factor 5. So now this base here needs to be distributed over the height. For that, what we do, we assume one of the method is to assume parabolic distribution. Other methods are based on the mode response. Parabolic distribution is why assumed, is very important. If we talk of the structure, if we take the structure and try to determine its mode shape using our Rayleigh-Ritchie method. Using the Rayleigh-Ritchie method, so then when we see with the parabolic structure, the mode shape of the first mode will also be approximately parabolic. If we look into the modes of the first mode of the free vibration of a structure, it will also come out to be parabolic. So this and the mode participation factor for first mode of the structure is nearly 90%. So these two combined gives me this parabolic distribution is going to give me a very good approximate solution to that of the what our modes will be there. What mode shape will be there and what distribution of the forces needs to be done. If the other methods are like you take the first mode, take the second mode, take the third mode, determine the values based on the first mode, second mode and third mode, and based on that then you go with the CQC, complete quadratic combination, that is the square of the first mode plus the square of the second mode plus the square of the third mode under root with take into count and find the base shear, the story shear. That's Q are the forces that will come at the nodes. So, and this also we take into how many modes to consider. Generally we take into consideration of first 3 modes or first 4 modes, but that depends on the mode participation factor. Mode participation factor is defined by 5 times K phi upon 5 times M phi, and that will give us some values for the mode participation factors. This mode participation factor should be greater than 98%. That is 98% of the response of the structure we are taking into count. So if we are not getting, we'll have to increase the number of modes. If we have lesser number of modes, and or if we have lesser number of, we require lesser number of modes, then also we can go with that CQC methods. So based on this, we get the shear forces, that is the story forces, and those story forces will result into our shear forces that needs to be resisted by the column. In this, try to understand one thing is very important, that we are nowhere these forces are nowhere going into the beams. We are nowhere considering the beams in the analytical method, or that it's in the code. These are mainly going into the columns as a shear forces, and that is to be designed for that. Now we come to plastic analysis. If you have any question till here, you can ask. No questions. Okay. So we'll move to the plastic analysis. Now, first thing, why plastic analysis is required is to understand. Generally what we see, we have seen that we want our structure to go into the non-linear hinge.
Sir,
And yes.
বলছি স্যার এমএস কি ইন্টেন্সিটিটা কি ছিল?
Sorry, I could not get you.
What is MSK intensity?
MSK intensity is like, if you look into the code, it is based on the both the effect of the earthquake as well as the energy content in the earthquake. Like what the effect of the earthquake is, that will define your intensity. What was the intensity? If we have like a structural damages, then that goes into higher intensity. The non-structural damages, that goes into lower intensity.
Okay, sir.
Now it is very much like, why plastic analysis? That is a big question to be answered. We have seen that we want our structure to go into non-linear range, and one of the simplest simplification of that is go with the plastic analysis. Like, that is easier to calculate with pen and paper. If otherwise all other analysis what we have in the non-linear range, we need to take into account the change of the stiffnesses value, that with that displacement, and the geometric nonlinearity as well, and that into consideration, then we need to go with the software basis. So in order to like not use the software, we go with the plastic analysis. I'll quickly move with the plastic analysis. I'll not discuss much on the plastic analysis. I have some large number of slides on this also. Generally, this steel behavior which we have is like, this is the first one is our like the general steel behavior which we take. So it is like this. We have already seen that there is a plateau region, and then there is a strain hardening. The actual stress, that is true stress, is somewhere like it goes above this. The engineering stresses are shown in this. One second. So based on this, but we idealize this with the elastic plastic region. That is, it is elastic up to the yield point. It is elastic up to the yield point, and then it is plastic. And this idealized stress strain curve gives us a good idea of like what will happen to the structure. We'll see how this is related to the pushover analysis. That we'll see when we discuss the pushover analysis, and when we look into the results of the pushover analysis and the elastic analysis. And one may note that this what discussion now I'm going to do, that is mainly for the steel structures, not for the concrete structure. In the concrete structure, there is a variation with that of the plastic analysis and the nonlinear static analysis. But for the steel structures, these nonlinear analysis and the plastic analysis nearly closely matches. So this you all would have gone through in your third year course. That is, we go with that once it is loaded, a steel structure is loaded, it is first in the elastic limit, the bending stresses distribution. Then if we load more, then it goes into the extreme fibers are in the plastic limits. And if we go on increasing, the fibers near to the extreme fibers goes into the elastic limits. Part of that is in the plastic elastic, part of the structure is in plastic. And if we go on loading more, then it will come into such that all the fibers at a point are in the is at the yield limit. And if we go load more, then there is a strain hardening, and that is why we have a failure at a larger value. So this is what is the map. So till this we have elastic. This is in elastoplastic region, that is the change of curvature takes place, and this is the plastic region. This is in the strain hardening region, that is this extra bulge at the for the stresses at the ends are going to govern as the strain hardening region. So this we have already seen. This one can look into this as like if we go on loading the structure, there will be a hinge, there will be a the extreme fibers will be in your elastic limits will yield, and then if you go on increasing the loads, it is such that all the fibers will yield, and this yielding will be like it is like beyond this. If we load beyond this you can rotate freely. Till there is all the fibers of a section are not in the not in the yield region, till then it can resist the forces. So now if we load more, the structure will fail. It is like there is a saying in the structure analysis that is a structure only collapses when it has exhausted all means of standing. That is like if we go on loading, like if we take into this one into consideration. So here we have like three possible locations of the hinges. That is, first one is here. First one is here, second one is here, and the third one is over here. So these, like first, if one of the hinges formed, still the structure can stay. The second hinge has also formed, the structure will still stay. But once all the three hinges are formed, then this will collapse. One may think of that we require degree of indeterminacy plus one number of hinges to finally collapse the structure. So that is all discussed in these slides. This will not be taking much into account because this already you all have studied. So it is like elastic region, then one hinge, then two hinge, and then the three hinge. It is like first it will have some elastic, that is the elastic modulus. Then one hinge is formed, then the elastic modulus will somewhat be lesser. Then the third hinge, and so on. So whenever you see a pushover curve also, that will also be somewhere like this. We'll come to that also. So in order to solve this, we require three different conditions. That is compatibility conditions, equilibrium condition, and moment curvature relations. These are the three which are required in order to solve this B problems. Then there is one of the method, that is mechanism method. Like we assume that these three locations will have the hinges, and then we try to equate using the work energy method, and that is one which we will use in the work energy method. That is the energy work done by the external forces will be equal to the work done by the internal forces. That is the moment, that is the plastic moments or plastic the points where we'll have the plastic hinges. There will assume a rotation, and that we can equate that and determine the moment carrying that the loads carrying capacity of the beams. So based on these like this also you would have gone through. That is, we have three different type of mechanism which is into consideration: beam mechanism, sway mechanism, and combined beam and sway mechanism. Now what will happen when there is one more thing what is to consider, that is like if we have a strong column, weak beam, then what will happen, the hinges will be formed on the beams. But whereas if we have strong beam, weak column, the hinges will be formed on the columns. So we want one thing, that the hinges are formed on the beams rather than that of the column. So in order to have that, we need to have the moment carrying capacity of the beams less than that of the moment carrying capacity of the columns. So if like we consider beam mechanisms, these are the two beam mechanisms, these are the two sway mechanisms. One thing you note that the forces acting in this are in the vertical direction for the beam mechanism, and forces acting in the sway mechanism is in the lateral direction. So if we talk of a simple structure, there is there is like a envelope that will come into this. We do not need to discuss. Yeah, this the sway mechanism. Now, one thing is very important to that is to be discussed, that for an earthquake forces, we want to be having beam mechanism or combined beam and sway mechanism. That is why we want our structure to be in elastic limits for our gravity forces. That is, if there is some dead load there or live load, for that we want our structure to be in the elastic region. So now only extra moment that is going to come from the lateral forces, and the lateral forces would never be accounting to the beam mechanism. That is, it won't be forming a mechanism in the beams. So what we do, we take into account only two things, that is sway mechanism and combined sway mechanism. So if we have a load distribution, now you see one of the important things is the load distribution, lambda W1, lambda W2, lambda W3. This load distribution is like a factor. So we can talk of these load distribution as that of the one can consider that this load distribution is parabolic. So that is taking into account our the first mode of the structure. So this lambda 1, lambda 2, lambda 3 will be somewhat like this, the parabolic which we have considered. It will be something like this. That is lambda 1, lambda W1, lambda W2, lambda W3. Now if we talk of this, we will have, there are, like, if we talk of the sway mechanism, there are 1, 2, 3, 4, 5, 6, 7, 8 hinges are formed. Each hinge will have a rotation of theta. So 8 MP into theta, if suppose all the columns have the same moment carrying capacity, that will be equal to this displacement, the delta which we have, into that is equal to the height of the one story into theta into W1 plus W2 plus W3. This theta also we can determine. If we want to, we can determine this theta. This theta in our earthquake engineering we take as 4%. Like that is the limit which the structure should at least go before the collapse. That is the 4%. So if we take into account this 4%, then we have an actual value of we get a value of lambda, or we can say that we can get the value of lambda easily by like here we have this theta is cancelling out. But if we talk of the energy, that we'll discuss further, that this 8 MP into theta, if we do not take into account this elastic, that is the forces, rather than this, we can take into account the energy of an earthquake. If we take into energy of an earthquake, we can determine this MP value, what should be there. But if we take into consideration that the forces will be in the parabolic range, will be parabolic, we take into account this way, and we determine MP values, what it should be. Now, if there are two different mechanisms here, that is the first story mechanism, that is the second story mechanism. If we take into second story mechanism, what is happening? We have again add MP into theta, then we have what? Lambda times, this is not going to contribute to anything into external forces. Only what is going to contribute H into theta is lambda times W2 into W3 plus W3. So out of this two, if we talk of this, lambda is going to be in this value is going to be larger, W1 plus W2 plus W3. So what will happen to lambda? This lambda will be smaller. So this it will fill in this mechanism rather than this, subjected to condition that the moment carrying capacity MP of both is same. If MP has a ratio, like, then it may happen that the building fills in this mechanism rather than of the other mechanism. Now there is one more thing, that is like this is going to have a positive rotation, whereas this goes with a negative rotation. Here this goes with a positive rotation, this goes with a negative rotation. So if we talk of the joint, there is a hinge at this, if it combine these two mechanism, there is a hinge formation at both the level, this and this. But we have already seen that the beams has the lower moment carrying capacity that of the column. So these two, if we try to balance the moments, so we have 1 MP over here, 1 MP over here. So what will come out, that this will become equal to 2 MP. But this is much more less than that of the moment carrying capacity of these two. So this, rather than formation of hinges at this place, hinges will be formed at the beam ends. So this is the one of the combined mechanism. In this, there is a hinge cancellation. That is, instead of 2 hinges, there is 1 hinge formulation. If we talk of like taking both MPs, moment carrying capacity of the columns and the beams as the same, we will have the hinge cancellation and will come to like there will be hinge cancellation of 2 MP. So instead of formation of this, there are very much chances of to formation of this. So based on all this, like we now need to decide which failure it is going to take. So for that, our designs will govern. That is the moment carrying capacity what we are going to give for each stories, that will be governing the which failure it is going to take. What we want actually to happen is that there is a complete collapse of structure rather than partial collapse of the structure for an earthquake. That we want this type of the collapse rather than the other type of collapse, so that the hinges are formed on all the beams and hinges are then formed on the base of the columns. So, and based on this, if it of lambda, that will give us the total forces that is coming into picture. Now, if this, and if we take into account our theta equal to 4%, we can also see, we can also make the graph that what is happening, that is the what is happening with the base shear. This will result into the base shear, and this will result into the displacements. So based on this, we can say that in which mode it is going to fail and what is the value, what is the total. If we get the lambda value and if we multiply this by lambda, we will get the total base shear. So we get two things from this plastic analysis. We can get one is the base shear and one is the mechanism in which it is going to fail. That is the preferred where all the hinges can be formed. And this is all, in this we do not require any computer software. We can do it by our own hand calculations. Then the other method comes is the plastic analysis. In the pushover analysis. In the pushover analysis, what we do? We generally give a displacement to the structure, and based on those displacements, we determine the forces that the structure is going to have, and that is the base shear. And we try to determine base shear versus the proof displacement curve. Then we superimpose this curve with that of the elastic response spectra demand. And then we determine that will this fail or not fail. If our elastic spectra demand is such that it is beyond this, so that means that for this structure it is going to fail. If our demand is over here, like if we have something like this demand, then this is the performance point which we will have, and that will be the displacement what we can expect when we will have the earthquake. For this again, we have a force distribution assumed, that is either we have based on the weights or based on the height, that is triangular, or based on the modes, any on one of the three, or based on the, like we can talk of the parabolic nature also, we can consider that also. More what we consider, we try to consider the possible locations of the hinges. So possible location of the hinges are column ends and the beam ends. So we try to check out for non-linearity in the beam ends and column ends only. We treat the whole structure to be elastic rather than that instead, and we assume only non-linear or inelasticity in the column ends and the beam ends only. So we define the hinges that this is always is done on the some of the softwares. Some of the softwares that are those are like we can do it on SAP 2000, or we can do it on eTabs. Some people have done it on some people have done force analysis on STAD Pro as well, but that is a difficult job. A STAD Pro does not do much of the push over analysis. The non-static analysis is not that straightforward in a STAD Pro, whereas in SAP 2000 or eTabs it is easier. One may do the push over analysis in the OpenSys, that is a open source software. One may wish to do push over analysis in the Abacus or ANSYS. That is also possible, but those are mainly much more into the finite element analysis software rather than for the push over analysis, because that will take much more time rather than our other softwares. So what we do in this, we define the length of a plastic region. That is, we assume that this is the length where which can be the plasticity can come, or where our hinges can be formed. This length does vary from the 0.5D to D. That is depth, where D is the depth of the structure of the member. So 0.5 times, so this length of the plastic hinges like half of the depth to full depth, whatever we wish to, we can give. Once we have decided that these are the location of the plastic hinges, we try to give the gravity load. In this gravity load, we try to consider our gravity, that is the dead load, plus percentage of live load. That is like we generally give we give the seismic weight. We give the seismic weight now, and we do analysis, and we try to check that all the elements are in our elastic range. Then we apply with that, like the gravity load there, we apply a shear forces. That is, we apply a lateral load in the section. And this lateral load distribution will depend on what distribution we assume. It can be linear, it can be modal, it can be based on the weight, what we have discussed previously. So when we apply this, there will be all the elements will be firstly in the elastic region. We will apply this and we'll try to calculate the displacement at this point. So we'll go on increasing the forces, we'll go on checking the displacements. So still till now this is in the elastic region, there is no change in the stiffness. We'll have the displacement in the elastic region. Once we increase, then this point has come into the yield region. So this yielding, this has yielded. Now what will happen? There will be a change in the stiffness, and that will result in that will change in this. So this has changed the stiffness. That is, there is a decrease in the stiffness, and one of the point has some more points have reached the elastic limit. So now again it will change the stiffnesses, and based on those stiffnesses, again there is some extra points that has come into this, so it goes on changing the stiffnesses, and finally we get a curve like this. That is, we go on increasing the forces in this, we get to the displacement, and these locations we go on having the locations where we have different elastic properties, and based on those elastic properties we see that some of the points have gone into the plastic region, some of the points have not gone into the plastic region. So finally what we generally go with the displacement controlled push. Lateral force distribution is applied. Lumped plasticity. This one thing which we have assumed, that is the beam ends and the columns ends will only go into the plastic region. That is the lumped plasticity model. One may go with the distributed plasticity model as well. That is, you assume that the whole structure will go into the plastic region, but that will take time. That is time consuming in the sense that the software will check at each and every point that is it going for the plastic region or not, and that will be time taking. So but this Level plasticity model also gives a very accurate approximation of the solutions. So we go with the lump plasticity model in this. Then hinge properties are based on the FEMA 356. Now the new code is ASCE 4113. The hinges properties have somewhat changed as per American standards. Indian standards, there are no codes that gives you what hinge properties should be. So we follow the American standard codes for the hinge models. And finally, we get a base shear versus roof displacement, and this is actually called a capacity curve. That is, this there is nowhere we are concerned on the demands. We are moreover trying to determine the capacity that the structure can sustain. And this capacity curve, once superimposed over this, over the demand curve, that is the response spectrum curve, we get a performance point. That is this is the amount of displacement and the shear forces that will come if a earthquake corresponding to this response spectrum hits the structure. That is, the structure is subjected to an earthquake corresponding to a response spectrum compatible earthquake. Then this is the displacement that we can expect, and this is the base shear that we can expect. So if we try to like increase the Z value, this will go on changing. That is, we can go on adjusting this performance point, and we can also determine what is the maximum response spectra compatible earthquake, PG of the response spectra compatible earthquake that will occur then when the structure will fill. That is the collapse performance point. That is the once when the response spectra collapses with that of the collapse. Response spectra is somewhere having its ends cutting at the end of the capacity point. So and this is one of the method by which we can determine the collapse points. Now there is a based on these what we have seen. Based on these, there is like two things. That the one is here also what we are determining, that is the points, that is where we will have the inelasticity and the forces. So these two can also be approximately estimated by our non-linear static analysis, or sorry, pushover and plastic analysis. So the hinge locations and this base shear can also be determined by our plastic analysis. That is like the location of the hinges, whichever mode it is going to fill, that will be determined. Moreover, the summation of all, that is lambda wi summation, will give us the base shear. So we can determine what is the lateral forces. And if we look into this, if we take a building frame and we do a pushover analysis, we draw the curve, we see the spread of the hinges, that is where all the hinges are formed. That will come out to be approximately same as that of the mode in which, as per the plastic analysis, it is going to fill. Moreover, if we look into the base shear that is coming out from the pushover analysis, that will also be approximately equal to that of the mode shear, that of the plastic analysis. So while starting, in order to check that if someone has correctly done this plastic pushover analysis or not, one can go with the pen and paper calculation of the hinge, this plastic analysis. If they are getting the similar value of the base shear at which the building is collapsing, so then it means that it is somewhere very much comparable. Then that is a good approximation and good analytical model has been created. Moreover, the spread of the hinges also we can see. If the spread of hinges are almost similar. That means that we have got a good approximation of the actual model in the analytical model, and that is very much important while doing an analytical analysis. We need to always verify our structure with that of some of the analytical model. That is some of the pen and paper method, or some of the methods which are already tried and tested. And then we verify that once the model is validated, then we can go with our own whatever analysis we do. Or one may look into can go with the experimental analysis, and then compare with the experiment. The models can be compared with the experimental analysis, and you can then predict other responses of the structure. So experimental analysis is there are two different types of experimental analysis that people generally do. One is the full scale test, other one is the scaled model test. A scaled model test is using the dimensional similitude, that is dimensional analysis, which we have already gone through in our undergraduate courses, which you all would have gone through. So now we have 7 fundamental quantities. Out of that, we are going to use only 3 in our similitude model. That is length, time, and mass. These are the 3 which are used in our similitude model. Temperature, during our dimensional analysis is very important that acceleration due to gravity cannot be scaled. People do this in the soil modeling. People if someone has interest in the geotechnical engineering, there people do with the scale. In the scale model, they go with the centrifuge, and they try to decrease the acceleration due to gravity also there. But in the earthquake engineering, we do not touch the acceleration due to gravity. So one quantity we have already fixed, that is your acceleration due to gravity. Now other quantity, that is the elastic modulus. Now if we talk of the steel, we have elastic modulus of the steel, and if we talk of the aluminum, you will see that there is a close match of the elastic stress strain curve as well. That is the elastic stress strain curve is some in the ratio of that of the elastic stress strain curve of the steel. So generally whenever you go with the model scaled model test, generally we go with the aluminum as a material. So now we have a new material over here, that is ER. Then we have one quantity that can be reduced or increased is by modulus of elasticity. Then time. Length is another second physical fundamental quantity which has been considered, and the third is the acceleration due to gravity. These are the 3 physical quantities that has been considered in our test. Based on these 3 physical quantities, dimensional similitude analysis has been done, and we try to determine what is going to be the a factor which needs to be multiplied to get the actual values. So that is the time is by L length to the under root length, frequency 1 upon that of, then the velocity n is dependent on this length parameter. Acceleration due to gravity is is not being scaled. Then the acceleration, normal acceleration, also not scaled. The strains are dimensionless quantities, so this cannot be scaled. The stresses are scaled in the ratio of that of the elastic modulus has been scaled. A specific gravity we are not much talking of. Displacements is in the same model as that of the length. Forces, that will be depending on the elastic modulus. So based on this, one can go with the 1:8 scale model. That is the instead of the whole modeling the building, go with a 1/8 model, and then you can do you'll have to, like whatever earthquake we have, earthquake time which is there, we'll have to divide it by this value. So we'll get a, like, instead of running it for, like, if there's an earthquake for like 16 seconds, so we'll run it for 2 seconds. Will like the time period will time of the time stamp will be divided by 8, and then we'll run it like for 2 seconds. We run it for that earthquake in 2 seconds will give us will give us a solution, and that solution will be approximately what the whole structure would have experienced in 16 seconds. One of the scaled model that is reported, and this is reported in Lignos et al. In that, these are the columns and beam sections that was existing in the model. For that, the plates have been used instead of the W sections, and these plates are made up of aluminum plates rather than that of the steel plates which have been used in this. And this is the final scaled model. You need to like match the weight also, scaled weight that is, and in that case you need to have the extra weights to be added, and then you do a analysis. And when you do analysis, you get the results. You can like whatever results we have over here, we can use that in the normal models, and we can predict the behavior of the normal structure instead of the scaled model as well. So this is one way of determining the behavior of the structure for the earthquake. Another one is the full scale test. Full scale test also, I have got some videos as well as this from the Design Safe website. That is like generally a database where all the analyses done are stored, and one can register on that and get the actual data of the full test from there. So I've got some of the videos from that test. This is the plan of the building which is there, which has been taken into consideration, and this is made up of wood. This is the elevation. One of the major thing is that we need to have a different foundation than that of the one building was having, because when we need to place it on the shake table to give it a run. So in order to give that run, we need to have a different foundation than that of the actual structure. This is a shake table. This is the largest shake table in US, for which the analysis has been done. And these are 3-dimensional shake table. That is like there is one motion in this direction, another motion is in this direction, and the third one is the vertical. This is the structure which is to be tested. This is the model which is there. There is like one is in this direction, the other is in the vertical direction, and one is in the other third direction. So like all the 3 axes has been, like, you can model it. Generally the earthquake contents are also the 3 models. That is like you have acceleration in X direction, you have acceleration in Y direction, as well as acceleration in Z direction. So all the 3 directions can be like the shake table test can be done for all the 3 directions. So this is the like construction phase. Like you start with first the foundation, then you go with the structure, then the full structure is actually placed on the shake table which I had shown you before, and on that will give different level of earthquakes has been given, and it is seen how the different components behave. Now one thing is like, see, the dead load is okay, but for the live load, what has been done is extra dead loads, like in the terms like steel plates have been put on the structure, so that matches with the seismic weight of the structure is actually the seismic weight of what the structure will have when in operation. So this is the time lapse of the construction which I have got. So the foundation, we require to make the foundation and this is actually has to be strong so that this does not fail while our analysis rather than that of the buildings. And then you go on with the each story by story, you go on forming. And finally, this structure is to be, once made, this structure needs to be shifted to this structure needs to be shifted using the cranes to the actual shake table. This will have all the sensors, like different sensors locations. This will have different locations. Will have the sensor. Moreover, the cameras has been installed so as to get the data. And these sensors are mainly LVDTs and accelerometers. So once this has been constructed, this is placed over the shake table. These are the accelerogram positions which has been used. That is, these are the 5 locations on the roof as the accelerograms. Seismic weights, which I have told you, has been like extra has been kept on each level. This is the input energy distribution that has been taken into account for X. The input, that is the displacements of the different sections that has been taken into account while for the shake table test. These are the locations of the LVDTs. These LED, the lighted portions. These are the locations of LVDTs so as to get the modes of the vibration. LED sensors have been used. These are the different modes which has been like observed with us from on the shake table. Normal pre-vibration test, that is the for that we do a sine sweep test, and like sine waves are there at different frequencies, and these are the different modes which has been developed for which has been like when observed. Then this is given a run. And this is like a full run like of the earthquake. This is the duration generally of the earthquake, and you have seen how this vibrates. Now we'll look into the different angle, and one may see that there is like, if you look from the front, it may look like very small vibration is there. There is a video also there in which we have one room of the structure in which what will happen inside the room. That is, we'll see the nanostructure elements, how are they behaving. Right now, when we look into that, there is no like major structural element failure. This is the video of the roof displacement, how the roof behaves. This is the raw file. I hope there is something error with the video. One of the corner of the building, you see this room. Inside the room also we have a video of that as well. Then after whenever this once run, we generally inspect the building frames.
Everything in it work, minimal damage inside of the building.
you see now after this there are inspection of the cracks which has occurred. These cracks you see are on the non-structural elements. You would have read that the cracks will always start from the openings and then it will go, and this generally, so when we have the masonry construction, then you go with the reinforcement at the openings. If it is not if it is framed structure, generally we do not go with, and in that cases during an earthquake we have an non-structural crack which is developed. This is inside of the room. You will see how the non-structural elements are behaving. One may look into that the non-structural elements are like so much into the motion. If like you see from inside the room, there is a lot of vibration which has been occurred. One you can look into once again. There is a lot of like non-structural elements are falling and all. But if you look from the outside, that we have already seen, there was like not much of the vibration were seen in the structural element, but non-structural hanging elements or non-pinched elements are generally one which is going to fail most of the time. This is all that I have for the day. Thank you. So questions like if you have anything to ask, you can ask. If you have any question, you can ask.
So participants, you can post your queries in the chat box. Yes, any queries? So there is one query on YouTube chat box. Kindly explain slope method.
Slope method in the sense like slope deflection method. That is like
it has not been question is not elaborated.
one of the question there is like why pushover analysis cannot see. I have not said that pushover analysis cannot be used for the concrete structure. I said that pushover and plastic analysis we cannot match for the concrete structures. One can do the pushover analysis to get the capacity of the concrete structures, but doing a plastic analysis for concrete structure is very different. You need to need to take into account what is the positive moment carrying capacity, what is negative moment carrying capacity. If one want to look into plastic analysis of concrete structure, there is a thesis Altun task which can be referred for the plastic analysis of concrete structures.
Hello, good afternoon, sir.
Yes, Jitesh.
Yes, sir. I want to ask question. Sir, for earthquake resistant building, if LYB is to more than 3, then we provide expansion joints.
Yes.
How much gap it will? How much gap it will be? Either 100 mm, 250 mm, somewhere I see 275 mm. So, sir, how we can decide, sir, how much gap it will be, sir?
See, that will depend on the structure length. That is like generally what is taken is 4% rotation is taken.
Yes,
So
sir.
now the height is if like 10 meter, then 4% of 10 meter will you can go with like it will come out to be nearly 40 mm
Yeah.
or 50 mm that you need to give.
So it depends on height, sir, also.
It depends on the like if you look into the code, there are two values. One is
Yep.
0.4% and another is 4%. 4%
Yeah.
it is like for the non-elastic region, that is if we take into account the like till 0.4% it has to be in the elastic limit. So if you take
Yeah.
0.4%, that will be the amount of the expansion joint you need to give.
Thank you, sir.
Last query. Do we do these tests on high-rise buildings or earthquake zones or any construction always?
Generally, what we do, we go with the analytical models and do that for the high-rise buildings. One of the video which I have shown is like a very like actually what is there that we cannot go with the so many buildings and go on going with the destructive test. That is we go with the say table test, we destruct the building. That is like so much of the cost consuming. So we go with the analytical models, and we go with the analytical models whenever we design. We need to go with first the analysis, that is both incremental dynamic analysis, time history analysis, as well as pushover analysis. Pushover analysis gives us a capacity curve. With that, we go with the response spectra compatible earthquakes. Like generally, we take a suit of earthquakes. Generally, at least there should be 6 or 7 earthquakes, and that should be matched. That should not actually be directly be provided in the building, but actually it should be matched corresponding to our response spectra. And for that, there are so many attenuation softwares which are there, which can be used to match your earthquake to a given spectra. One of them is Sysmomatch, which is academically free. So generally what I use, that is Sysmomatch, for in order to like match the earthquakes to our response spectra, and then that is used for the analysis.
Okay, thank you so much, sir. So it was very impressive. The animations you showed, they were really very nice, and I was really hooked to your lecture. It was very interesting, and we gained a lot of knowledge about earthquake resistant structures. So thank you so much, sir. Thank you for accepting our invitation and coming there for this presentation. So thanks a lot, Dr. Shashi Narayan.
It's my pleasure, ma'am. Thank you for the invitation.
Okay, so that's all for this session, participants. So we will be having our next session at 3 o'clock by Dr. Joy Pal from NIT Hamirpur, and he will be talking on structural health assessment. So please join by 2:45 p.m. So that's all for now. Thank you.
Thank you, ma'am. Thank you, sir.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
slideshow mode, we could see the slides such that they still are remaining small in size. If we could see it in such a fashion that the slide is visible properly.
So,
like we could see even the next slide.
Acha, at the right side, na?
Yes, sir. Yes, sir. If you could remove that, then I think it will become enlarged.
Is this okay? Is this okay now?
Sir, it still remains small. If it could be magnified, I think you could use the option for magnification. Oh, it is cutting.
Display duplicate is okay now?
Yes, sir. Yes, sir. It's fine now.
Okay.
Thank you. Thank you.
Okay.
Sorry for interrupting.
No, it's okay. So now, and it was reported that some engineers has also marked some cracks in the pillar on April 6. So just around 2-3 months earlier to the accident, or April 30. So this is what happened in the case of this bridge. And this is not only the one case. If you see the collapses of infrastructure or buildings in the Google, you will see that a lot of structures failed. So some more structures I am showing you here. That this is the Injaka bridge collapse over the Injaka bridge, over the Injaka river. This is Sheumshu bridge collapse, I-35 bridge collapse, and these you know very well because these are very new collapse at Mumbai or in Thane. Reason found for this Injaka bridge collapse was aging of the structure. This is improper welding for the Sheumshu bridge and I-35W bridge because of poor maintenance. And more importantly, I would like to say here that these bridge collapses 6 years just after completion of its construction. So you just imagine. And these are already, I think, poor maintenance is there and aging was also the effect. So the important thing is that because of these collapses, life safety becomes an issue. A lot of people died because of these collapses. So this structural health monitoring is mandatory or essential if we want to optimally use the structure, if we want to increase the reliability of the structure. And definitely as a civil engineer, we do not want the catastrophic failure, right? We want ductile type of failure. So if it provides some indication so that before the collapse, we can evacuate the people. And we will definitely get some alarm or a time so that we can retrofit the structure so that the remaining life can be extended or we can strengthen the structure. Right? Finally, it will give you the life safety. So these are the requirement, or these are the motivations for which the structural health monitoring is required. So I'm giving you just some two figures that let us say by observing our body, it is sometimes difficult that what is happening inside the body. By observing, we can say that this people is fit, but maybe something happens in its inner parts, right? So what we are doing, we are basically going to doctor for periodical checkup, and he will carry out some tests and identify whether there is any problem or not. The same way, although you may see that the structure is looking good from outside, but still you have to periodically monitor the structure so that you can get the idea what is the condition of the structure or whether any damage is there or not. Therefore, the structural health monitoring is the process of implementation of damage detection strategy in order to identify the condition of the structure. So here I am using one term, that is damage. So from where this damage is coming? Damage means it will start at the material level. That means at the beginning it is very small, then it will propagate, and then ultimately the structure will collapse. And this damage will basically change the or affect the performance of the structure or behavior of the structure. So this is what we are doing in the structural health monitoring. So this structural health monitoring can be categorized in 4 stages or 4 steps. One is called a level 1 type structural health monitoring. Second one is level 2 type of structural health monitoring. Then level 3, then level 4. What is level 1? Level 1 means it is entirely qualitative. That means you will not get any idea about the quantity of the damage, or you will not get any kind of information that where the damage is. It is somewhat like you went to the doctor and doctor told that maybe you are having some problem by observing your or carrying out some kind of normal physical testing. They will say that it is qualitative measure. There is some problem, so you should go for further testing. So here you will get only the idea whether damage is there or not. Then second one is level 2 category damage, that where this damage is taking place. That means whether damage is at the liver or damage is at the kidney or any other places or not. So that means in case of structure, whether damage is at the joints, whether it damage is at the normal members, whether damage is at the slab or damage is at the column. So this kind of information you will get in case of damage localization. Coming to the quantification part, that means you will quantify or severity, that what is the level of damage. If some member is affected, then what is the severity of the damage. So that you will get in the level 3 category damage quantification. And last one is that prognosis, that is prediction that how long this structure can sustain. So this is what is or these are the things which are basically the category of the structural health monitoring. So for monitoring the structures, various techniques are available, and broadly we can categorize these techniques as local technique and as global technique. Here only 3 I have mentioned: ultrasonic wave propagation based technique, then visual inspection, then scanning. It is not like that only 3 is there. Some more techniques are also there. Global techniques, vibration based technique is there. So it is found that normally the local techniques are basically time consuming, labor intensive, and it is difficult to monitor a large structure. While vibration based techniques are less time consuming, less laborious, and useful for civil engineering structure. So I'll come to that part in detail. And these figures you can see here, these are the studies which have been carried out in structural health monitoring and retrofit lab at IIT Bombay. So now coming to the local techniques. So I'm starting with visual inspection. So it is very simple and straightforward thing that you will go and you will check the structure. So now it is not that much easy also, because it requires a lot of experience. Extremely experienced person can identify the things. So he has to go there, he has to check every point, importance points, and then he will conclude. So you can now understand that how much time is required, how much experience is required, or one important thing I would like to mention here, that the joints of the steel structure, these members are so heavy that by using hands only you cannot understand that whether the bolt is loosened or not, and the joints are the critical location where damage commonly occurs in the steel type of structure. So this is one thing. Another one is inaccessible point. Like some locations are there where you cannot reach. So that location, from that location you cannot get the idea. So ultimately some unreliability issue is there because of these parts. And moreover, one another thing, that you cannot give any quantitative measure. It is entirely qualitative measure. Because of this, NDT came into picture. It is non-destructive testing also. So in NDT, these techniques are there, but a lot of more techniques are there, but I am just showing you few techniques only. So with these techniques, the health monitorings are carried out. So let us see one by one. First one is acoustic emission. So acoustic emission क्या है? Like you are having a structure and you can see that here source is mentioned. That means source means where the crack generates. That is the source location. So this point is the highly stressed point. So when cracks will generate, there will be sudden release of energy. That energy will travel through the material as wave, and some sensors are placed here. So this sensor will collect the waves and it will store the data using the data acquisition system, and then some signal processing thing you will do in order to find out the damage location. So common example, railway track monitoring we are doing with this. So you can see some acoustic emission sensors. Yes? Any question? Am I audible to you?
Yes, sir. Yes, sir.
Okay. Okay. Shall I continue, na?
Yes, sir. Yes, sir.
Okay. Okay. So here you can see that some sensors, acoustic emission sensors are placed here, and this location is the stressed location, and because when load comes here suddenly some cracks or some damage occurs, and because of that damage these elastic waves generated, and these waves are collected by this sensor and it is stored in the data acquisition system. So using that you can monitor basically real time. That means your sensor is placed that at what time this damage is occurring you can identify, or even whether it is propagating or not you can also identify that. But again problem is that it can monitor very small area, so that it is not that much suitable for monitoring a large civil engineering structure. Now coming to the next part, that is ultrasound. So here the thing is that two probes are there that you know very well, I think. One is source. So earlier case, if you see that the signals were generated or the waves were generated because of sudden release of the energy. But here you are giving some kind of excitation to the structure. That means you will give the load to the structure. And another probe is there, or transducer is there, which will collect the response of the structure. So thing is that if there is any crack, then it will reflect and it will come to here. So like this way, you will basically identify whether damage is there or not. Another example I would like to give you, that you might have seen this kind of thing, that is UPV testing, which is carried out for identification of the quality of the concrete, right? And even IS code is also there, that what is the velocity of the UPV through the concrete. So if void is there, then velocity will be less. If void is not there, then velocity will be high. So like this way, you can monitor the structure. But the point is that civil engineering structures are quite large structures. So at how many locations you are going to use this UPV testing? Now coming to the third one, that is guided wave based technique. So guided wave based is also one kind of ultrasound thing. That means 20 kilohertz, frequency is 20 kilohertz, more than 20 kilohertz. So here you can see one plate I have shown here, just to give you some idea that how it works. I have placed one example here. That is, this plate is normally used in the aerospace structure, and this is called honeycomb sandwich structure. At the top, one skin layer is there, that is, it is kind of plate. At the bottom, same plate is there, and in between, aluminum made honeycomb type of structure is there. And in that plate, at some location, these honeycomb cores are made dense. Because if some locations are there where electrical appliances are required to fit, or some other like two members or other things are required to join, so at that location, these high density cores are made. And another thing, that as there is three things, one is top layer and bottom layer, and here is the middle, that is sandwich wala part. Okay, so there will be a chance for disbonding. That means disbonding between the skin and the honeycomb. So if this thing happening, this disbond is happening, then it will propagate and ultimately it will collapse suddenly. So this is, for this is, you need to monitor or identify whether it is working properly, whether it is, there is any disbond or not. But problem is that normal structure, if normal core is there, there will be some kind of signal. If there is some changes, then there will be the variation of the signal. So if there is high density core, then what will be the change? If there is disbond, then what will be the change? That is what we need to find out. Because high density core is not the damage. If you are considering that this is the damage, then there will be some problem. So that is why two different studies are carried out. So here these 1, 2, 3, 4, 5, 6 are the sensor location, and these sensors are piezoelectric transducer, and with one transducer you can give the actuation or the signal, that is guided wave you can give, and with the others you can collect the data. And here I have plotted these signals, that what you received. So you can see here that when HD core is there, the amplitude reduces. You can see amplitude of the signal reduces. Moreover, when separate modes are coming, you can see that at different modes it is giving different response at the HD core. So here you can see also that the signal reduces, signal strength reduces, while in case of disbond it increases. So this is the thing, So by observing this thing, you can identify that which location is the disbond location and which location is the HD core location. So HD core location, we need not to be worried because it is okay. But when it comes to the disbond location, that means I need to change this thing, or I need to think about this portion. So this is only the time history data. So you can apply some kind of signal processing thing like wavelet transform, where you can get more idea about this data. Just see that what is the structure type and how many sensors you have placed, and now consider about the civil engineering structure. So you can understand that how much sensors or how many sensors are required and how much time is required. So it is also little bit very difficult to apply it in the civil engineering domain. So now coming to the another part, that is laser hydrometer. This is also very sophisticated equipment, and this is also carried out in IIT Bombay. So this equipment is basically laser hydrometer, and you can see that laser point is given at this point. So that means when it will vibrate, it will collect the data from this point only. And you need to make a program, computer program, so that this laser will move to different points to collect the data. So once all the data are collected because of this vibration, then it can automatically use its algorithm to find out the mode shapes, to find out the natural frequency of the system. So by comparing the natural frequencies and mode shapes, you can find out the damage location, or you can identify what is the damage quantity. The benefit is that it is not a contact type of sensor. So it is directly, I cannot say directly that it is local, it can be global, but the point is that if you are benefit of that when the structure is complex or inaccessible point is there, then also this laser point can go at that part and collect the data. This is the benefit. But disadvantage is that how many locations you are going to collect this data. So it is considered, it is a cantilever beam. So cantilever beam, at this cantilever beam you have to collect so many data. So think about this civil engineering structure, that how many locations, from how many locations you need to collect the data, or how much time is required. So that is why some other techniques came into picture, that is called global methods, and mostly vibration based techniques are considered. Static techniques are also there, but point is that if I want to give a static displacement to a structure, civil engineering structures, huge force is required, and that is why it is not that much popular. So vibration based techniques are usually employed as a global health monitoring technique. In the vibration based health monitoring techniques, again the techniques are divided into traditional techniques, then modern techniques. So starting with the traditional techniques, lot of techniques are there. Few popular techniques I am showing here, and this is just to say that how the damage indexes are calculated. Damage index means if damage index value is high, that means that location is damaged. If damage index value is less, that means it is not the damaged location. That is what it is. So various techniques, that modal curvature, modal strain energy, curve fit, kurtosis, FRF curvatures are there. The important point I would like to show you here, that here D is there. D means one is damaged structure. That means if you are having a damaged structure, you are collecting the data and you are compared with the undamaged data. So that means you have to depend on a undamaged structure, and in reality, civil engineering, getting undamaged structure is also very tough. Anyway, let us see that how these techniques performs with an example. So this is a small scale frame structure, and you can see that it is resting on a shake table, and accelerometer is fitted to the structure, and these acceleration response are collected. As a damage, here only 2 centimeter damage is given, and we would like to see that whether these traditional techniques are able to find out the damage location or not. So please keep it in mind, I am showing here only one damage structure, but like here, damage and undamaged comparison, that means I have to carry out one undamaged experiment also. So we have given the acceleration here, and we collected the data using the Catman Professional. This is the data acquisition system. Then you can see when we applied the algorithms at the damage location, it is showing the peaks. So by observing the peaks only, you can identify, or you can say that the locations are damage location. But problem is that apart from the actual location, some other peaks are there. So this is because of experimental noise. Here is also damage, here is also damage, here is also damage. So that means you can be confused. Then you require the undamaged structure. So these things are there, and that is why some other techniques came into picture, that is called model-based technique. So in model-based technique, I am just saying you 2 type of health monitoring, or 2 category of health monitoring. One is level 2 category, another one is level 3 category. So we all know now that level 2 means localization and level 2 means quantity estimation. So what we need to do, we need to prepare a numerical model for this structure. You have to prepare the numerical model so that it can represent the structure very well. So that numerical model becomes the reference structure. Okay, so that reference structure will be utilized in order to identify the location of the damage. So here, using that numerical model, you will compare with the damage structure, and you will apply that model curvature technique, FRF curvature technique, and other things which I showed earlier in order to find out the location. And in case of level 3 damage detection, what I can do, in the numerical model, I will fix some parameter based on our experience, that yes, these are the parameters where damage, which is sensitive to the damage. So based on that parameter, we will update the numerical model until it represents the damage structure. That means at the position or at the time when our updated reference structure producing the same response of the damage structure or the real life structure, that time I can say the parameter value is the severity of the damage. So when I'm talking about now updating operation, that means here optimization technique comes into picture. So that means we will basically construct an objective function, and that objective function will be minimized or maximized by updating the variables, and ultimately when it represents both the same structure, that time we will finalize the parameters value, and like this way the severities are estimated. So one problem of this optimization technique is that if number of variables are more, then it may give you the less accurate results. So that is why sometimes what people do, they are basically identifying the approximate locations and then using only few parameters, they are updating the operation. So combinedly, this called hybrid techniques. So I am not going to show you the hybrid techniques because if you know these, understand that this localization, application of localization technique, and if you know the model updating technique separately, then you can easily understand that what is hybrid technique. So I am now going to show you that how the severity of the damage can be identified using this finite element model updating technique. So let us consider this frame structure. It is also resting on a rigid base, and as excitation we are giving impact here, and different type of sensors are placed. So this is the representative or schematic diagram of this frame. Here you can see that bolted connections are there. Here also bolted connection is there. Here also there. So at 6 locations bolted connections are there, and we have placed 6 strain gauges at these locations. Okay. So this is and the bolts are made hand tight by using hand only, and full tight by hand tight plus the half turn of the bolt. So like this way we have tightened the bolts. Okay, and these are the damage conditions that we have created. So let us say the first case at this location, that means here bolts are hand tight at this location, bolts are hand tight and the rest of the bolts are tight, full tight. Then we made this is full loose and rest of the bolts are full tight. Like this way at different locations we have created a different type of damage. And now we want to apply the model updating technique to find out that what is the effect of this damage in the parameters. So let us see that how we can do this. So first we collected the strain data here, and you can see from this strain data that initial portion is not effective because it is the noise, and after this also very noise is there. So that means this part and this part is not that much effective, and at this location very high peak is there. That means this position is the point of application of the impact. So I am ignoring those parts. So in between I am taking some portion of the signal which is shown here. So this is the effective portion of the signal. Then I compared damaged signal with the undamaged one, and you can see that how the responses are varied. Now one representative numerical model I constructed here. See, this is the bolted joint. So here in MATLAB you cannot directly create the bolted joint, right? So joints, this is the bolted joint, so there may be some rotation. So that is why some rotational springs are considered. That's because if loosening is there, then there will be some kind of rotation. So that is why rotational springs are considered. So here you can see this is the model which I developed in the MATLAB. So at this location, one rotational spring I put, here also another rotational spring, here also another rotational spring. Like this way, all 6 locations rotational springs are considered. So the fixity of the rotational springs is the parameter, because if it is loose then fixity will be less, and if it is tight then fixity will be more. That is what it is. So that is why this spring stiffness will directly give me the value of the loosening of the bolts. So then next step is creation of the objective function. We already discussed that how to consider the or how to construct the objective function. So our response was strain time history. Then we converted into the frequency domain, and we used that directly here. And then in order to give more importance to the natural frequencies, we have used the maximum amplitude separately in the objective function. Side by side, we are giving one weight factor. Weight factor will, what it will do? It will basically give you more importance to the sensor which is very near to the damage location. So this is how the objective function is considered. And in here, two variables are there. One is gamma LRC and gamma RRC. These are the fixity factor value. So LRC in the sense that this member, this spring is LRC and this is RRC. For this member, this is LRC, this is RRC. For this member, this is LRC and this is RRC. So here gamma LRC means 3 and 3 variables, and gamma RRC matlab 3 variables. Total 6 variables are there. But ultimately what I consider that, okay, as these springs are very tightly fixed and from both the sides it is fixed, so I ignore these two things. So only with the 4 values I have formulated the objective function. And then I first try to see that what is the fixity factor value for the undamaged case. As because I have given only hand tight plus half turn of the bolt, that is why I got the fixity factor value 0.56. In this context, I would like to mention that fixity factor value, if it is 1, that means it is fully tight, that means infinitely rigid connection, and if it is 0, that means it is pin connection. Okay, so that means originally, or which we are saying our undamaged structure, this is basically semi-rigid structure. So this is the baseline of our structure, and you can see that mostly all are very near to each other. And variation is because we are giving the tightening using hands, so that is why some variation is there. And then we carried out the model updating operation, and for each cases we have determined what is the fixity factor value, and then we determined that what is the differences or percentage changes in the fixity factor value. And you can see that at every location, you can see that at every location, the higher values indicates the location of the damage and quantity of the damage, that it is 27% less than the original one. So this is how the model updating technique works well. So now if you can consider, or if you have any other structure, you can apply the same way, same process, then you can identify what is the quantity of damage and what is the location of the damage. Just only one thing, parameter you have to choose very judiciously, because if your objective function is not that much sensitive to the parameter, then it will give you erroneous results. So before selecting the parameters, you check the sensitivity with the objective function, then only use that one. Okay, and success of this technique again depends on the modeling accuracy. So now using the vibration based technique, some other type of studies are also there. At this moment, this is my research area, or I am working in this area only, that is machine learning based technique. So machine learning based techniques, various techniques are again there. So this is what I am considering, that is image based deep learning technique I am currently considering. So idea is that first I have to have some data set based on which I will train a machine or network, and I'll keep it for future reference. So in future, if I am getting some data from different type of structure, I will give it to the machine, and machine will recognize that whether it is undamaged category, whether it is damaged category, or if it is damaged category, then at which location it is damaged. So this is what we are trying to do. It is somewhat like if I can see a bird, I can recognize that it is a bird. How? Because my mind is trained, or my brain is trained, that if these kind of features are there, that means it is bird. If this kind of features are there, that means it is tree. So like this way, we are also creating or generating a network in which we are training the network through some information or features and saying that if these features are coming, then it is this category. If this kind of features is coming, then it is that category. So like this way, the things are done. So it is not like that always you have to use the images. So you can use data also, but at this moment I am considering image-based technique. So we know now that this is the data, effective portion of the data that I collected earlier. So this data, using that data, I converted into time frequency plot and I saved it as JPG image. So now I got my image. And these images are quite big, So if you use this image directly to the machine learning algorithm, then it will take huge time. So in order to avoid that, what we are doing, we are resizing the thing or resampling the thing from here. So this is the resized photo you can see, or image. Now another thing you might have heard, that machine learning requires huge amount of data. Why huge amount of data is required? Because for a particular kind of object, let us say if I am having one apple and its color is red, then I trained like this, that if red color and this is the shape, then it is apple. But if I am giving green color and same shape, it cannot identify, because my mind is not trained. So that is why some variation in the data is required, so that you can categorize this thing. So variation from the data, how it will come in our structural health monitoring, because numerical analysis or experiment you can get only one data. So if you want to create the large image set or large data, you need to add some kind of noise, and this is using this different level of noise we have created the image set. So now my data is ready. So you can see here now how did I generated the images. So total 5 cases I have considered, not the 7 cases like earlier, only 5 cases I have considered. And for each case I generated for training 72 images for each case, you can see here. So once the training is done, then validation will be carried out and then testing will be carried out. Now what is validation? Actually, when the machine is trained, so after each iteration, it will check with some images that how much accuracy it obtains. So this is how the validation is done. And testing will be done after entire completion of the training and validation. So here 24 images are considered. So now this is how the deep learning works, that we will give the input images, and then this input image basically it will take as the pixel values, and here one convolution layer is there. In the convolution layer, some kind of filtering operation will be done. After filtering, then some kind of sampling will be done. That means some important features you will collect from this. Please keep it in mind that in the convolution layer, different type of filters will be used to get the important information. And then again, another filtering will be done to get more important data. Once you got this important data, then further you can do the same operation so that you can get more and more important data. So how many layers you will consider, that is totally up to your problem. After that, this part is basically your classification part. In softmax layer, basically some kind of, it will check that whether the probability of a particular object or particular image is more than a threshold value or not. If it is more than threshold value, that means it is for a particular class, or else it is not in that particular class. So like this way, the classifications are done. When this classification is done, then I have given the testing images. So in the left side, you can see the category of the testing images. So I have given the 24 images of ED1 category, and computer or the machine identifies these 24 categories as same category. That means 100% accuracy here. In case of ED2, I have given as ED2 category, but 20 out of 24, 22 is identified as ED2 category, while 2 is identified as ED3 category. Like this way, all the things are done and we are getting very high accuracy results and quite satisfactory thing. So only one problem is that you have to have a strong database, then these techniques can be employed to the real life structure. Another important issue is that if the structure is changes, then you have to again retrain the system, because boundary condition, geometry will require the retraining the network. So by observing these things and other things, you can see the current challenges. That present challenges are in the structural health monitoring is that the slight damage, or you can say that insignificant damage, right? So if insignificant damage are there, then it is very difficult to recognize. So this is one kind of problem. And why it is difficult? Because insignificant damage is not significantly affecting the lower modes. So this is the problem. Then feature selection. In the model updating technique, I have explained that features should be such that so that it can or it is affecting sufficiently to the objective function, or it can affect the objective function, significantly affect the objective function. Suppose you are considering some features which is not at all affecting the objective function, or if it is not affecting the damage parameter, then it will be difficult for you to identify the damage location. Now another important thing, that civil engineering structures are different. One structure is different to another structure. Even two similar type of structure is also not having the same responses. If you vibrate these two structures, then you will also get different vibrations. So there is not at all a particular technique which will serve cure all to all. No particular technique named. So for every structure you have to think about different, or every structure you have to consider the technique first, then you can go for the testing. Then sensor deployment, like you have placed some sensors in a particular location where the damage is not creating that much effect, or where the response is not significant. So that is why sensor deployment is also an art. You have to first carry out the study that where should I put the sensors, and then you can place the sensors. Another problem is that because of damage, some changes in the response is coming. Response in the sense, in the signal or the data you are collecting from the structure. So because of damage, if some changes you receive in the data, this kind of changes you can also find if operational or environmental variability is there. So this is also a problem. And at the last, that it requires long period of monitoring, because if you want to see the performance of the structure throughout the design period, so you require or long time period monitoring. So you need a robust system so that you can monitor the structure for the long time, and you can get a strong database of the structure. So these are the present challenges where you can also work in future. So with this, I would like to conclude here. And if you have any questions regarding this, so I'll be happy to answer. Thank you.
Thank you so much, sir. First of all, for accepting our invitation for delivering such a wonderful lecture on structural health assessment. I'm sure that this topic is going to have a lot of MTech and PhD students for deciding their topic of research. And thank you so much. And if any student have any doubt regarding this lecture, then he or she can ask. Please write down in the chat box. So there is one question in the chat box.
How SHM system can be installed? So actually many techniques are there. Am I audible to you?
Yes, sir.
Richa lady. She asked me the question. Actually, many techniques are there. I am telling you one thing, that one thing is that if you monitor a structure for long period of time, so you can place some contact type of sensors in the reinforcement bar. Let us say you are considering a girder or a beam structure, so you can place a sensor or paste a sensor in the reinforcement bar. After that, construction process will go on. And then some wires will come out from the concrete, and that wire can be connected with the data acquisition system. So periodically you can collect the data and you can check that how the beam is performing. So like this way you can install the system in the structure. Anything else?
No, sir. Thank you so much.
Okay. Thank you. Thank you very much.
Thank you, sir. Thank you very much.
Okay.
Thank you, sir. Thank you so much.
Okay.
Thank you, sir.
Okay, madam.
Thank you, sir.
Thank you, sir. Thank you.
Thank you, sir.
Thank you, sir. Thank you, sir. Given important times for us.
Okay, students, tomorrow we will have our lecture at 11 a.m. And the speaker will be Sunil Kuntia, Dr. Sunil Kuntia from NIT Rourkela. Thank you so much.
Thank you, ma'am.
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 मैम फीडबैक फ्रॉम कहाँ मिलेगा? Thank you, sir.
Sir has gone.